Some time ago, I watched a video by this guy, whose last name I definitely know how to pronounce, about procedural mesh generation using marching cubes, and I remember using every second of that day trying to get the algorithm up and running. A few months back I stumbled upon my crude implementation from all those years ago, and it was not very good to say the least. So, in this video I will walk you through the basics of this technique. If we begin with some function that takes in a 3D point, does some math or follows some algorithm to convert this 3D point into a single value, we can then sample it at all integer points within some range. We get what's known as a voxel grid. The voxel grid is a one-dimensional representation of a three-dimensional grid. I've also heard it being called a flattened grid. Either way, it makes it possible to store three-dimensional data contiguously in memory when using a collection type that is stored on the heap. The alternative would be to nest collection types. This would result in a pointer to a pointer to a pointer to floats instead of just a pointer to floats. If that made no sense, Google it. Maybe you'll learn something. Reading a value from a flattened collection requires a bit more work than a nested one. To not have to write this every time we read a value, I will instead create a struct that stores the collection and the resolution. This also removes the need to pass the resolution as a parameter every time you pass the grid, since we now bake them into a single variable. We begin with the new function, which simply creates a voxel grid containing a pre-allocated vector with a capacity of resolution cubed, and the resolution itself. Now we create a read function for this struct that simply indexes its own data with the appropriate equation and returns what's returned. Furthermore, we can also give the ability to push to the grid by simply forwarding the request to data. The sampling of the scalar field now looks like this. I will now hide the positive points, because they're really just in the way for the next part. Just know that they're still there. I'm just choosing not to render them. This also represents the final product better, as the goal of the marching cubes algorithm is to generate a mesh that perfectly encapsulates these points. Now we iterate over every point, excluding the extremes. In this nested loop, we will call a function that we'll define soon. For now, there is one thing that I've skipped, and that is the mesh definition. As you can see, we pass a mutable reference of the mesh vertex positions into this function, and the reason why I skipped the creation of it is because depending on what graphics API or game engine you use, the mesh definition will look drastically different. So I'd rather just send you on a hunt in documentation than try to make some generic thing that won't work for everyone. Anyway, now we'll define the marchCube function, which as shown earlier needs three things. The current XYZ point, which we get from the nested for loops, access to read the voxel grid that we created earlier, and access to modify the mesh vertex positions. If you're unfamiliar with Rust syntax, I'll try to give a quick explanation so that you'll be able to implement this in any language you'd like. The point has the type of tuple, containing three unsigned integers, and is being unpacked to three individual variables in the function's scope. The voxel grid has an ampersand before its type. This means that it is a reference to a variable above this scope, because we don't want to copy that entire thing. The vertex positions vector just contains positions in 3D space, and in my case, those are represented as arrays with 3 floats each. As you probably noticed, it says mut after the ampersand, which stands for mutable. Most programming languages make their variables mutable by default, which means that you probably haven't run into this that much. But maybe you're more familiar with the keyword const, standing for constant, which makes a variable not mutable, aka immutable. What's important is that this function can edit the variable above this scope. The reasoning behind this is that we want to be able to call this function a bunch of times, and by the end we will have a vertex positions vector that has been filled with all the vertices that this function deems necessary. Now, before we can begin with the actual function, we need some data. I suggest that you either define these statically in global scope or in a static class. The first array is used to pair up an index from 0 to 7 with its offset in a cube from the bottom left rear point. If you're wondering, I'm using a coordinate system that has x to the right, y up, and z forward. For reasons you will hopefully understand later, we also need to be able to get coordinates for points along the edges between these points. A cube has 12 edges, every edge has 2 points, therefore we will have another array that stores the 12 corner index pairs. Now that we have our data, we can begin with the marching. The idea of the algorithm is to create a mesh that ensures that every active point is inside and every inactive point is outside. This means that every point has two possible states, active or inactive. We can therefore represent every single configuration of this cube with a simple 8-bit number, where 1 is active and 0 is inactive. The first bit therefore represents if the 0th corner should be inside or outside the mesh. This also means that we have 2 to the 8, or 256 different configurations, 256 different meshes that could be created in this cube. Now you might be wondering how we're going to figure out all of those, but luckily we don't have to, because we have the power of the internet, and I'll leave a paste bin in the description that has all the configurations. Now that we have the 8-bit configuration number and our array of triangulations, we can use that configuration number as an index into the triangulations. This triangulation now contains up to 15 indices from 0 to 11 each, and we begin by creating a for each loop for these indices. This will then be used to index into the edge array. We now get 2 indices back, and we in turn use those to index into the points array. Now we get the actual vertex position that the original triangulation wants us to create by taking the average between these corners. Now we push this vertex onto the vertex positions, and we're done. Of course, now you'll have to create some sort of thing that'll take these vertex positions and display them in the world as a mesh. But with all that, we get the most primitive version of marching cubes. There are a lot of things that I would like to add, like making the mesh smooth instead of bumpy, but sadly I'll have to end the first one here, because this video is taking me way too long to create, and if I go on any further, scope creep will actually follow me to my grave.